Have you ever stopped to think about how moving a simple magnet could, power an entire city? It honestly sounds like something straight out of a fantasy novel, but it's one of the most foundational principles in all of physics, Faraday's Law of Induction. So today, we're going to pull back the curtain and see how motion and magnetism connect in a way that, and I'm not exaggerating here, literally changed the world. All right, let's set the scene. We have to go way back to 1831, to the lab of a brilliant experimentalist named Michael Faraday. See, he was completely obsessed with this one single profound question. And the experiments he built to answer it, well, they were about to rewrite everything we thought we knew about electricity.
So this was the central mystery. At the time, scientists knew that if you ran an electric current through a wire, it would create a magnetic field. That was pretty much old news. But Faraday wondered, could it work the other way around? Could a plain old bar magnet, with no batteries, no power source, somehow conjure an electric current right out of thin air? He was absolutely determined to find out.
Okay, so check this out. This is Faraday's first major breakthrough. He takes a simple bar magnet and he pushes it into a coil of wire. And just like that, boom, the galvanometer, which is basically a super-sensitive meter for detecting electric current, the needle jumps. A current has just been created in the wire, seemingly from nothing more than a little bit of motion.
But here's the twist, and this is the really crucial part. As soon as Faraday stops moving the magnet, as soon as it's just sitting there, perfectly still inside the coil, the current vanishes. The needle on the meter just drops right back to zero. Poof! The magic is gone. This tells us something absolutely vital. The magnet by itself isn't enough to do the trick.
So the natural next question is, what happens if he pulls the magnet back out? Well, the current reappears. It's back! But look closely. This time the needle on the galvanometer kicks in the opposite direction. And that means the current is now flowing the other way around. So clearly, the direction of the motion matters. A lot.
Okay, so let's recap what Faraday figured out. A current only shows up when the magnet and the coil are moving relative to each other. It actually doesn't matter which one is doing the moving. If you move it faster, you get a bigger current. No motion, no current. And, as we just saw, the direction you move it in determines which way the current flows. The big, huge takeaway here is that it's all about change.
But, saying it's all about change is a little vague for physics, right? How do we actually measure this change? We need a better tool than just saying the magnetic field is passing through the coil. And this brings us to an absolutely essential concept called magnetic flux. So what on earth is magnetic flux? Well, think of it like this. Imagine you're standing in a river holding up a fishing net. The magnetic field is like the water flowing in the river, and that coil of wire is like the open mouth of your net. Magnetic flux, then, is simply a measure of how much water is flowing through your net at any given moment. And we can see that idea right here. Magnetic flux, which we represent with the Greek letter phi, really depends on two main things. The strength of the magnetic field itself, which is shown by how dense these blue lines are, and the area that those lines are passing through. The more lines you can cram through a certain area, the higher your flux is. Now, the full-blown mathematical formula can look a little intense, I know. But don't worry. For most of what we're talking about, where the magnetic field is nice and uniform and it goes straight through our coil, we can use a much simpler version. Magnetic flux is just the magnetic field strength, B, multiplied by the area, A. That's it. Simple as that.
And of course, like any good quantity in physics, it has its own special unit. We measure magnetic flux in Webers, named after the physicist Wilhelm Weber. So 1 Weber is just what you get when you have a magnetic field of 1 Tesla spread out over an area of 1 square meter.
Okay, so we've got our key concept down, magnetic flux. Now that we have this tool in our toolbox, we are finally ready to state the beautiful, elegant physical law that explains everything Faraday saw in his experiments. So, here's the law, just put into plain English. The induced voltage, which physicists like to call electromotive force, or EMF for short, is directly related to how fast the magnetic flux through that circuit is changing. You see, it's not the amount of flux that matters, it's the rate of change. That's the secret sauce. Oh, and that little negative sign? That's super important too. It's a reminder that nature always creates a current that tries to oppose the change that's happening. And this is it, one of the most important equations in all of physics. That little epsilon symbol, epsilon, stands for the induced voltage, and the d phi b over dt part,
That's just the fancy calculus way of saying the rate of change of magnetic flux over time. Remember when Faraday pushed the magnet faster? He was just making that d phi b over dt term bigger, and that's exactly why you got a bigger voltage.
But what if you want an even stronger effect? Well, that's easy. Instead of just one loop of wire, what if your coil has n turns? Each and every one of those turns experiences that same change in flux, and all those little voltages they generate just add up, so the total induced voltage gets multiplied by the number of turns in your coil.
All right, all this theory is fantastic, but let's make it real. Let's get our hands dirty and actually apply Faraday's law to a real problem to see exactly how this thing works in practice. Okay, so here's our setup. We've got a square coil made of 200 turns of wire. We know it has a total electrical resistance of 5 ohms, and we're placing it in a magnetic field that's getting weaker over time. It's decreasing at a rate of 0.40 Teslas every single second. So the big question is, what current gets induced in this coil?
We're going to tackle this with a simple 3-step game plan. First, we have to figure out the rate of change of the flux. Second, we'll plug that right into Faraday's law to find the voltage it creates. And finally, we'll use a good old friend, Ohm's law, to go from that voltage to the actual current that's flowing.
Okay, time to crunch the numbers. We're solving for the induced voltage, epsilon. So we start with negative n, which is our 200 turns. Now we need the rate of change of the flux. Since the coil's area isn't changing, this is just the area multiplied by the rate of change of the magnetic field. Now the problem told us the field is decreasing at 0.4 Teslas per second, so we have to make that rate a negative number. We plug all that in, and we get our induced voltage, 0.080 volts.
We're almost home. We've got the voltage, but the question was about the current. For that, we turn to a classic, Ohm's law. Current is just voltage divided by resistance. So we take our 0.080 volts, we divide it by the coil's 5 ohms of resistance, and that gives us our final answer, a current of 0.016 amperes. We did it! We just calculated a real electric current, created purely by a changing magnetic field.
And that brings us right back to the single most important idea from all of this. It's the dynamic, ever-changing nature of that magnetic field passing through the loop that actually generates the electricity. If there's no change, there's no current. It's that simple. And that one single principle is the foundation behind pretty much every single electric generator on this planet.
So, we've figured out how to create a current. But let's take this one step further, okay? We know that when a current flows through a wire that has resistance, it generates heat. So that leads to a really interesting new question. If you wanted to generate heat at a specific rate, say enough to warm up your hands on a cold day, how quickly would you need to change that magnetic field to make it happen? Now that is where the physics gets really, really cool.